In this video, I want to introduce the CMOS D-Flip Flop. Now, we will design the D-Flip Flop using inverters and tri-state drivers. Now, here I've shown the tri-state driver that we described in a previous video, but let's recap here in case you didn't see the previous video. So this is the input to the tri-state driver, and this is the output. And I want to explain two different modes of operation for this tri-state driver. The first mode is when this PMOS transistor is on and the NMOS transistor here is also on. That's shown by this symbol for the tri-state driver. Here I have the gate of the N FET set high and the gate of the P FET set low. And under this condition, the tri-state driver behaves like an inverter. The circuit is equivalent to the inverter operation, and I call this the inverter mode. Now, the other mode of operation is when this P FET transistor and this N FET transistor are both in the off condition. So when the gate of the N FET is low and the gate of the P FET is high, both these transistors are off, and the equivalent circuit has the output that is detached. So here we have part of an inverter. The P FET is not connected to the N FET, and this circuit essentially does nothing. And I'm going to refer to this mode as the off mode. But before we describe the operation of the D-Flip Flop, let's present the concept of circuit delay. Here I've drawn three inverters in series. I've labeled the input of the first inverter in. The output of the first inverter is labeled A, and the output of the second inverter is labeled B, and the final output is labeled C. So let's analyze what happens as I change the input voltage as a function of time. And here I'm plotting time on the horizontal axis and voltage on the vertical axis. So this input starts at 0 volts and it switches high or to a logic 1. And perhaps this is 2 volts depending on the level of the power supply. Let's analyze what happens at node A. As the input to the first inverter switches high, the A signal will transition to a 0 level and it'll stay low. And when the A signal switches, the B signal can switch to a high level. So the B signal will start out at a low level and it will switch to a logic 1 level and stay there. Now that allows the signal C to change from a 1 level and then transition to a 0 level and stay at a 0 level. So we see here that the first inverter has a certain delay shown here. The second inverter has this delay, and the final inverter has this delay. So the circuit does not respond instantaneously. It takes time for the signal to propagate through these three inverters. Now, if the final inverter, for example, had a long metal connection, let me change colors. If it had a long metal connection, this long connection would introduce some stray capacitance that would slow down the switching time of the node C. Now perhaps node C goes to several other circuits. Perhaps it drives several other inverters, and each inverter adds a little bit of capacitance to the node C. And all this capacitance will cause the node C to respond slower. So with this added capacitance, instead of falling quickly, this node C may discharge very slowly to its zero level. The more capacitance that is added, the slower the response of the node C. So hopefully this gives you some idea of circuit delay, which will become important when we analyze the D-Flip Flop. So now let's start to take a look at the D-Flip Flop. Here I've shown two signals. At the top I've shown a data signal, and below that I show a clock signal. And below that I show the symbol for the DFF. Now this data signal here is this input to the D-Flip Flop. And this clock signal is this input. And notice that my data signal can be changing during this time. And then there's a stable period here. And again, the data can be changing. And then I have another stable period for the data. And what I want to do with this D-Flip Flop is when the clock signal transitions from low to high, I want to grab this data and present the data at the Q output and the NQ output. Now, for example, if the data input is a 1, when the clock signal transitions high, this 1 will be transferred to the output Q, and the not Q will be the opposite signal. It will be a 0. Now, if I have a 1 or a 0 for the data signal, and clock transitions high, a 0 will be transferred to the Q output, and the not Q will be the opposite. It will be a logical 1. So let's consider how we can design a D-Flip Flop so that when the clock transitions high, we grab the data. When this later clock transitions high, we grab this data. Here I've drawn part of the D-Flip Flop circuit. And if you recall from a previous video, this circuit is a latch. It has an input data here that gets transferred to the Q output when the clock signal goes high. So for example, when the clock signal is high, this first tri-state driver is in the inverter mode. So it allows the data to transfer into this latching circuit. Now when the clock signal goes low, this tri-state driver goes into the inverter mode, and the other tri-state driver goes into the off mode, and the data is locked in these two equivalent inverters. So again, when the clock is high, the data can come in. This tri-state driver is in the off state. When clock goes low, the data is reinforced in this latch, and the data is locked out from the input. So this is only part of the D-Flip Flop. So let's show the rest of the D-Flip Flop. So what I've done here is I've repeated this latch circuit at this location here. And the D input to the D-Flip Flop is here. The Q output is here. The not Q is the Q output inverted through an inverter. and my clock signal is here, and the NC signal is connected by name. I've not drawn in all the wires. The C signal is connected by name, so the connection is inferred by the name. So I don't need to draw all these wires. It would be rather messy. But one thing to notice is that this input tri-state driver is in the opposite state of this latchback tri-state driver. So when this input tri-state driver is in the inverter mode, this other tri-state driver is in the off mode. It's not doing anything. And notice that this tri-state driver is set opposite to this tri-state driver. So when this tri-state driver is allowing data to come in, this tri-state driver is in the off condition. So let's see what happens here. Here I've drawn the data signal at the input. I've drawn the clock signal here. And when the clock signal is low, the data is allowed to enter this first latch, but it's blocked from entering the second latch. It can't get any further than the two equivalent inverters, this being the first inverter, second inverter. But when the clock transitions high, what I do is I shut off the data source. I put this input tri-state driver in the off state, and I allow the input tri-state driver of the second latch to pass the data onto the Q and the not Q. So let's analyze the timing. So this is the time, the instant when the clock transitions from low to high. When the clock signal is low, it's allowing the data to transition in. But I have a certain timing requirement here. The data has to be stable ahead of this clock signal changing from low to high. And this time period is called the setup time. So this data has to be stable before this clock transitions high. And that allows the data to propagate through to this point here. Now, if the data doesn't have time to propagate to this point and my clock changes, I could have garbage data, and I'm not sure that the data would be correct. So I have to allow enough setup time for this node to become stable. And then my clock can change to a high level and allow the data to propagate through to Q and not Q. I also have another timing requirement that's called the hold time. So the data has to remain stable for a short time after the clock signal goes high. And this is called the hold time. And I need the hold time because when my clock goes high, I'm shutting off this tri-state driver. And that doesn't happen right away. I don't want any bad data to sneak through when I'm trying to shut off this first tri-state driver. So I need the data to remain valid for a certain hold time. So hopefully this gives you some idea of how the CMOS D-Flip Flop works. It's basically a latch combined with another latch to allow the data to be sensed at the edge of the clock and then be transferred to the Q and the not Q outputs.